In section 2.5, and I'm just going to call this, it's not what our book calls it, but logic and proof. So what I want to start with is, I've mentioned in the past, everything okay, Jordan? Yeah. You can sit here, please. What we mentioned before was that logic, that geometry, what we're studying is called Euclidean geometry. And back Euclid in ancient Greece, Euclid came up with what we know about geometry. And the amazing thing about Euclid is what we start with 5 what we call common sense statements. So 5 postulates. The postulates are something that we accept as true without proof. We've talked about that before. And Euclid started with 5 postulates and 23 definitions. And from those few things, those 28 things, built everything that we know about geometry, essentially. So just from that little foundation, built all we know about geometry. And what Euclid did, he was really one of the first people that made a system of putting these things together with logic, step by step with logic. So that's what we're going to start doing, is putting things together step by step, and we're going to give reasons for why we know that we can do these things. And the purpose of doing that is to learn how to make an argument using logic. How do we know that what we're saying is true? Well, I can say this because of this. And that's really what we're doing. That's what proof has to do with. So we're going to start with something that should be a little bit familiar in algebra, is solving equations. So we're going to list some properties that tell us why we can make the steps when we solve equations in algebra. So these first are called our properties of equality. So when things are equal, these are things that we know are true. We're guaranteed that these are true. So all of these are properties. So I'm just going to write property once, and then everything else is going to be a property after this. So if A equals B, if two numbers are the same, then we can add the same number to both sides of the equation. A plus C equals B plus C. So that tells us we can add the same thing to both sides of the equation. That's our addition property. And then we have subtraction. It tells us the same thing. If we have two numbers that are equal, then we can subtract the same thing from both sides of the equation. We do that all the time when we solve equations in geometry. We add something to both sides, or we subtract something from both sides. Multiplication. Again, we're starting with two numbers that are equal, and I'm going to just leave off the then here. If A equals B, A times C equals B times C. I can multiply both sides of the equation by a number. And we do that all the time when we solve equations and division. And these are all properties. If A equals B, and we call them properties of equality because we start with these things that are equal. We can divide both sides of the equation by the same thing. That's what our division property says. And we have to make sure we're not dividing by 0. And the other thing we do a lot when we solve equations is substitution. And substitution means if A equals B, we can replace A with B in any equation. So we do that a lot of times when we solve for x, but then, for example, when we solve for x, then we have to find the angle. We did some problems like that. And then we substituted x back into the equation for the angle. So that's what we do when we substitute. We're using the substitution property. So these are all the steps that we take when we solve equations. We're just giving them a name. So the reason that we know that we can do these things is because of the addition property. Because of the subtraction property, multiplication property, etc., etc. We have a couple more properties that allow us to rearrange things. So this is how we solve equations. We can also rearrange things. This next one is called reflexive. Reflexive property, again, another property, tells us that A equals A. Any number is equal to itself. The symmetric property says that if A equals B, I can write it the other way. I can turn it around. So we do that a lot of times when we solve our equation. We write our answer at the end with x equals rather than something equals x. So we can turn our equation around the other way. And the symmetric property tells us that's why we can do that. The transitive property. The transitive property is kind of like what we just talked about yesterday with when linking to conditional statements. A equals B and B equals C, then A equals C. So we're linking these two equations together. A equals B, B equals C, so A equals C. That's a transitive property. And then finally, the distributive property, another one that we use a lot when we solve equations. A times B plus C equals AB plus AC. So we're going fishing the way a lot of us learn this one. A distributes to the B and the C. And I can also write that with subtraction. B minus C equals AB minus AC. So that's called the distributive property. So all of these properties are the reasons that we can do the things we do when we solve equations. So what we want to do is start practicing constructing a proof by something that's familiar. We're going to solve an equation and say, here's how we know that we can make this step. That's what we do when we build a proof. Here's why I know this is true. I know this is true because of such and such. So when we're doing a proof, we're using deductive reasoning. We start with something that we know is true, and we're figuring out step by step what has to be true if this thing that we know is true is where we start. So let's show how we might construct a proof using these properties. And when we use them, I'm not going to ask you to say property. You can just say subtraction, multiplication, division, substitution, that kind of thing. And the reflexive and the transitive properties, those will come in a little later. So does everybody have these properties? Okay. So let's look at an example of how we use deductive reasoning, how we link what we know is true to the next thing that we know is true, and provide reasons, provide an explanation of why we know it's true. So our reasons in a proof are going to be postulates, definitions, or properties. So I'm going to start with this drawing. And we'll say this is 2x minus 15 degrees. Let's measure this angle. And this angle is x degrees. And we want to find x. So basically we're going to break down this problem into steps, just like we would solve it, but we're going to give a reason for each step. So what do we know? What do we know about these two angles? They add up to 180. So my first step is I'm going to say x plus 2x minus 15 equals 180. How do we know that? Why is that true? It's a straight line. What did we call these two kinds of angles? They're adjacent. They're adjacent angles. We gave them a special name also. They're supplementary. And they made a line, so we called them a, what kind of pair? Linear pair. So my reason is, I could say linear pair and supplementary. So that's how we know they add up to 180. They're a linear pair and they're supplementary. So we're saying we know that's true already. All right, what would we do next in this equation if we wanted to solve for x? Add 15 to both sides. So I'm going to say x plus 2x equals 180 plus 15 is 195. So what property are we using when we add 15 to both sides? Addition. We just added 15 to both sides of our equation. So that's the addition property. So I'm not going to make you write addition property. What we did was add 15 to both sides. Now what do I do? So I add 2x and x, and I get 3x equals 195. We could call that a property. I'm going to say what we did, you could say it's not really the addition property because we didn't add on both sides, but I can just say add. We just added. Now what do we do? Divide by 3, so x equals 195 divided by 3. And what property did we use there? Division. All we did was divide by 3 on both sides. And I could rewrite this. 195 divided by 3 is 65. So x equals 65, and so that's our. So we went through this problem step by step and gave a reason. This is how we know. This is how I know I can do that step. The addition property tells me I can. But here I just did addition. I know I can add. Here the division property told me I could do that. So that's how we build a proof. We say we know this is true, and then the reason is we give a reason. Here's how we know that this is true. So not too bad when we're doing these properties with solving equations. So questions on that example? All right. So the properties of equality that we just talked about are for numbers. They're for numbers and equations. If we're talking about shapes, Then we need properties for congruence. And they're very similar, but this is going back to what we talked about in chapter 1. We compare numbers by using equal signs. We compare shapes by using congruence. So we're going to list some properties of congruence. Some of them are kind of the same, but they have to do with shapes. So let's look at our properties of congruence. There are not as many as there were for equality. So we're talking about figures here. We're talking about shapes. Our figures are shapes. So we'll start off with the reflexive property. And I'm just going to write one property once. So the reflexive property tells us that figure A is congruent to figure A. Any shape is congruent to itself. The symmetric, and this is just like the reflexive property. I just want to point out, this is just like the reflexive property for equality. A number is equal to itself. A shape is congruent to itself. The symmetric property says if figure A is congruent, and I'm going to start using FIG for figure B, so we don't have to write quite so much. Figure A is congruent to figure B, then figure B is congruent to figure A. So it doesn't matter which order I compare them in. I can turn them around and compare them in either order. That's our symmetric property. Sometimes it's convenient to turn our order around. And then the transitive property works just like the transitive property that we just talked about. If figure A is congruent to figure B, we're going to link congruent shapes together basically. And figure B is congruent to figure C, then we can figure out, just figure two different ways there. Figure A is congruent to figure C. So we just link one to the next, just like we did with our law of syllogism, and just like we did with the transitive property for equality. We're linking one to the other by putting them together. So those are our properties of congruence. So what I want to do is practice, do some examples talking about picking which property might tell us something about a step we took, and then we're going to put together a proof using these properties. So are we all good on this? I'm going to spend a little time on this, so it's a lot of information right up front. So we'll spend a little time on it. It's not something that you're going to memorize right away. We'll spend a little time on it. All right. So here's my example. For all of these, I want to know what property justifies my step. What property tells me I can do this thing? So if I start with 7x plus 3 equals 24. And then I write 7x equals 21. What property tells me I can go from here to here? Subtraction. I subtracted 3 from both sides. So that's my subtraction property. Segment RS is congruent to segment ST, and segment ST is congruent to segment TU. I'm going to say RS is congruent to segment TU. So what property am I using there? Transitive. I'm linking these two together. Transitive links two things together. So this would be my transitive property. And if we were being technical, we would say transitive property of congruence. Transitive property is fine. How about 5x equals 10? So 10 equals 5x. Which property is that? Symmetric. And symmetric does come from symmetry. I'm just turning it around. It doesn't matter which direction, it's the same. We're saying it has symmetry. The equal sign has symmetry. The same on both sides. That's a good way of thinking of it. So that would be my symmetric property. So this, if we saw these things, this was how we would be justifying. This is how we would give a reason. Those would be our reasons. All right, so let's look at these properties. Let's link them together. Let's put together a proof of something. So proof, when I say a proof means that a proof is an argument. And we're using deductive reasoning. So deductive, starting with something we know is true and figuring out what else must be true. So basically our proof is just an argument with deductive reasoning. And we use proofs to show that conjectures are true. We said conjectures, something we think is true. Proof shows that it is true. And how do we show a conjecture is false? Someone said it. Counterexample. So proof shows a conjecture is true. A counterexample shows that a conjecture is false. So let's make a proof. Most of the proofs that we'll do in here are called two-column proofs. And all that means is we're going to put our statements in one column and our reasons in another column. That just helps us keep track of them. Most of the time, if mathematicians, other types of, if you're actually doing a proof, you use what we call a paragraph proof. You just make an explanation. We're going to do two-column proofs to try to keep our information all straight. So here's our example of our proof. I'm going to start with a segment. And I'm going to label my points A, B, C, and D. And what we know here is what's given to us. Given to us means we know it. That length AC equals length BB. So it's the same length here, from here to here, as it is from here to here. We want to prove that AB equals CB. So let's look at this really quickly. and get an idea, a picture of how we're going to make our proof. Well, this whole segment here is AC. And we know that's the same as BD. What is in common between these two segments? From here to here and from here to here. What do they share? They share B and C. They share that little segment in between. So the idea of our proof is we're going to say if I subtract the length of that segment from the whole thing, from this whole thing, and I subtract the length of that segment from that whole thing, if we start with things that are equal, if I'm subtracting something that's equal, I end up with something that's equal. That's kind of the outline of our proof. So let's write this out. So I'm going to put my statements over here and my reason over here. So that's what I mean when the problem asks you to do a two-column proof. It just means put your statements in one column and the reasons in the other. This helps you keep things organized. So I'm going to start off with my given. AC equals BD. And my reason over here is given. We know that. Well, now I'm going to say AC is made up of two smaller segments. AC equals segment AB plus segment BC. Now, do we remember? It was a little bit back when we said we could add two smaller segments together to get a bigger segment. Remember what we called that? We have segments, and we're adding them together. We had a postulate called the segment addition postulate. So our reasons for proofs are postulates, properties, or definitions. So a segment addition property tells me I can add two smaller segments to get a bigger segment. I'm going to do the same thing for segment BD. BD equals BC plus CD. The idea is we want to get something where we can get rid of this piece that they share in the middle. And this reason is the same thing. Segment addition postulate. Tells me I can add two smaller segments to get a bigger segment. Well, up here this tells me that AC equals BD. Well, here's AC and here's BD. So if these two are equal, what does that tell us about those two things? They have to be equal. AC and BD are equal, so these two have to be equal. So AB plus BC equals BC plus CD. And what we're doing, what we can say we're doing is I'm taking this and substituting it for AC. I'm taking this and substituting it for BD. So this would be substitution. I'm taking this thing and I'm putting it over here for BD. And I'm taking this thing and putting it here, substituting it here for AC. So that would be substitution. Well, we said our goal was to get something where we could subtract this part that they share in common from both pieces. Well, don't we have BC on both sides of the equation now? So I'm going to say AB equals CD. I subtract BC from both sides of the equation. And I'm going to put in parentheses BC from both sides. And let me highlight here where we did our substitution. This is AC, and this is BD. So I substituted that there, and I substituted that there to get this equation. So there's how we construct a proof in geometry. Now what you're going to have to do in your homework, you're not going to have to do this all from scratch. The homework will have it set up a little bit, and then you have to fill in a reason, you have to fill in a statement, so you're finding kind of missing pieces of the puzzle. Eventually you'll be able to do some a small proof on your own, but for now you'll be filling in pieces of the puzzle. All right, questions on that? So this is just our first, we're kind of dipping our toes into the idea of using logic and putting together something that a logical argument that proves something is true. All right.